All right, so in this lecture, we are going to march down. We have marched down to this eigenvalue section on the abstract side. And then we noticed that we had the spin 1/2 ad hoc introduction. And in this lecture, we're going to focus on this material right here. We're going to talk about the Pauli two-component formalism as an alternative to the Dirac formalism that we used. And the reason is because in QED, we lean strongly on this Pauli two-component formalism. And in order in particular to solve the Dirac equation. So we're going to really focus in on how this works and the correspondence between the Dirac formalism and the Pauli two-component formalism. And it should be quite seamless, right? These are literally just different ways of writing down the same stuff. And it's just which architecture is most convenient for the problem at hand. So that is our goal for today. And let's begin. So we begin by identifying a way of establishing a basis for a 2D vector space. Whenever our 2D vector space is a state space of a quantum system that has two dimensions. So the state space has two basis vectors. So any vector, any state of our quantum system can be expressed as a superposition of two basis vectors. And in particular, we're going to use the spin projection basis vectors. So we know that if we have a spin 1/2 system, there are two eigenvalues of spin projection, plus 1/2 h bar and minus 1/2 h bar. That's because the total spin is 1/2, and we know that the projection can go from plus 1/2 to minus 1/2, but it has to go in units of 1, and ergo there can only be two spins. Now, I know we didn't literally redo the entire theory of quantum theory of angular momentum. So this is something you need, I presume you know from quantum mechanics, right? That's a prerequisite, just to be clear. But to understand the Dirac formalism for this, we take these two eigenvalues. Instead of labeling the states by the two eigenvalues, which is implied here, we're going to label the states plus and minus, and we know that the actual eigenvalues are going to be 1/2 and minus 1/2. I'll set h bar equal to 1 for the purposes of this. So the spin projection operator on the plus state gives you 1/2 plus. The spin projection operator on the minus state gives you minus 1/2 times minus. Right? So this is the Dirac formalism that we're going to overlay the Pauli spin formalism, or the Pauli two-component formalism on. But we know that a general state, which we'll call chi, is some superposition of the two basis states, the plus state and the minus state. And C1 and C2 are complex numbers. They're interpreted as amplitudes for the probability of measuring plus 1/2. We'll see that in a second. And the probability of measuring minus 1/2. These are the amplitudes for those probabilities, which means the magnitude squared of these complex numbers are the literal probabilities. Now notice I use chi here. Chi is a very popular symbol for a Pauli two-component spinner, and it shows up a lot in the study of supersymmetry. They use chi, they use psi, and they use, I think zeta are popular. But anyway, we're going to go with chi for now to get familiar with these particular Greek letters. So the bra associated with this ket comes down to us through the basic rule where the bras are bound to the kets through the inner product, and ergo, when we flip the bra, we get the complex conjugate of the components, and we get the corresponding bras to the kets of the state. And what we're going to do now is we're going to replace these two basis vectors with these column vectors, these two-dimensional column vectors. And that is a one-to-one replacement, right? We are now going to think of this object here as this literal 1, 0 column vector. And this formalism, we're going to now duplicate this formalism with these two column vectors. The first thing we understand is that if we're going to make this literal replacement, then this needs to be our literal replacement for this ket expression up here. But the beauty of the formalism now is that in the ket expression, it's totally abstract. You can't add the plus to the minus and come up with something else unless you just give it a name, right? The definition of this addition is that C1 times the up state plus C2 times the down state is equal to psi. And this defines this addition property, right? So every time you do an addition in the Dirac formalism, you're basically defining that addition by giving a name to a new thing. But in the matrix formalism, we know how plus works, right? If you have two column vectors, you can literally just add them component by component. And so we can literally execute this addition and get the literal definition of psi, the state chi, not psi, chi, as a column vector with two complex numbers. So this is now a complex vector space. And notice it's a complex vector space because C1 and C2, the scalars are complex, right? The vectors that define the complex vector space, the basis vectors, they're just two symbols that we're choosing to be these column matrices. What makes it complex is the scalars that multiply these guys, right? So this element of a complex vector space is very conveniently and tightly written in as a column vector, which is a lot easier than this. Well, for this purpose, it's a lot easier. And so this is the advantage, is we can define what this plus operation is. We have an arithmetic that allows us to work with these column vectors. And by the way, this would be true for any dimensionality, right? We're focusing on 2 because we're talking about spin 1/2. But if we were talking about spin 1, you would have 3. If you're talking about spin 3/2, you would have 4, right? So you could do this for any dimensionality, but we're going to focus on the Pauli spin 2-component formalism only uses 1/2. But the interpretation is exactly the same. The magnitude of C1 is the probability of finding a plus, the plus state for the operator SZ, and the magnitude of C2 is the probability of finding the minus state when we apply the operator of SZ, right? So that this normalization, this leads to the notion of normalization, right? And that's true for these guys here in the Dirac formalism. It's true in the Pauli spin 2-component formalism. But the 2-component formalism has a beautiful advantage in that we can write down this normalization equation as a vector equation, as a matrix equation, right? We take the adjoint of our state, and this adjoint of the state multiplied by the state using the arithmetic of vector multiplication, the linear algebra stuff that you learned usually in your freshman year in university. When you do this multiplication, you could just write this down as the adjoint of our 2-component state times the 2-component state, where the understanding is you're executing the arithmetic using standard arithmetic, and you get C1 star C1 plus C2 star C2, which is literally what this is, and this equaling 1 is a tight statement of normalization. Here, normalization is a little bit harder to express. You do want to express it as the bra chi against the ket chi equals 1. So that's easy to express in this form, but to execute, you're going to have to write down this, right, to capture the mechanics of the normalization for this. Look, it's not terrible, but you're exploiting the fact that these guys have an arithmetic that you understand. You know what this plus means. You know how to execute this multiplication. So that's how we define basis for this 2-dimensional vector space. What we haven't described is how these operators work. So let's talk about that now. All right, so now we're talking about operators in 2D vector space. In this case, I'm not going to have the stuff appear as we need it. I'm going to leave it all on the screen and then just work through it. That way I can write a little more freely. But the idea is, we're going to review how in Dirac notation this works, and then show how we convert it to our new 2-component formalism. But if we have a ket chi, and we apply an operator f, and I think for this purpose we're going to presume f is an observable. So it doesn't have to be, but we apply some observable operator f. We're going to get a new state, right? The point of f as a linear operator is it takes a state and it converts that state into another state that's still part of the vector space of states, the state space. So we convert one member of the state space to another member. And it's kind of tricky. How do we name this other member? We can name it f chi and put it in a ket. That's the abusive notation thing we talked about last time. Or we can just call it chi prime, meaning prime is the state of chi after, or the label to the state of chi after f is applied, right? But this ket is a different ket than this ket, and the difference is directed by the linear operator. So we can study the new state, chi prime, by sticking in these complete set of states. Remember this operator that a couple lessons ago I was calling the you can't overstate its importance operator, right? This guy right here, right? Just this per point, right? With just n, right? That's a complete set of states on n. We talked about how that works and how sticking it into things is just adding unity. And we do that twice. We do it there for n, and then we also do it, we do it here for m. So we've actually put in 2. That's why we have a double sum here, right? And by sticking in these guys here, we end up with this notion right in the middle. First of all, we have m on chi, which is the projection. M and n now sum over, it's either plus or minus, right? So m starts out being plus, and n can be plus, or m can be minus, and n can be minus, right? That's just a way of saying we're summing over these 4 things, right? In fact, you could actually just write down, m goes from plus, minus, and n goes from plus, minus. So you're just summing over those 4 states. So actually, I literally did it right down here, didn't I? We showed the entire sum, right? So this first one, m is plus and n is plus, right? So you get, those 2 get replaced by the plus states. These 2 gets replaced by the plus states. This object right here, right, is the projection against chi of plus. So that would be, in our notation from the previous page, that would be C1, because if you put plus right here, right, you would get plus plus and then plus minus. That goes to 0, that goes to 1, so you're left behind with C1, right? So this guy here would be just a complex number, and that complex number would be C1. Likewise, this would be the complex number C2, this would be C1 again, this would be C2. Then this object here is also a complex number, because remember, f acting on the plus state returns some other state, and whatever that other state is, you contract, or you map it using the dual space mapping bra. You take it, whatever that new state is, you take its inner product with plus, and that's a complex number, right? Because this is a state, this is a new ket, this is a bra acting on a ket gives you a complex number. So that's a complex number too. So this is this here is a complex number times a complex number, so that becomes a complex number times a ket. So this ket is composed of this complex number times that ket there, and then this complex number times the same ket. So you can add these 2 together, right? And whatever this is, you add it to that, and you apply it to the basis ket, and that becomes one component. The sum of this and this becomes one component of chi star. And likewise, for the minus case, complex numbers again, complex numbers, and you get the minus case. So it all kind of hinges. We know what this is. If we know the state chi, we know what these guys are. But we need to know something about f. We need to know these numbers in order to understand how f acts. And that's the only way we can define chi in terms of the new basis. You can write this down as a sum here, sum over m and n of f mn, which are these numbers here, right? F plus plus, F plus minus, F minus plus, F minus minus, where these indices are now obviously these sort of symbols, right? But you're summing over all the possible pluses and minuses. You've got this m and n, but this guy over here is a complex number. So here's the complex number associated with these matrix elements. We call these matrix elements, by the way, and this is why, because it looks like a matrix. And this is a complex number, and then this is the final resulting basis ket. And so this is already, even in the Dirac formalism, this looks like a matrix, and that's why we call them matrix elements regardless of the formalism. So now if we switch over to the Pauli formalism, right, we're looking now at a spinor, chi, right, which is a two-component object, which I'm going to call this object right here, chi1, chi2. And chi prime is now some two-dimensional matrix, 2x2 matrix, that acts on our spinor and returns a new spinor, and that new spinor is chi prime. So there's some matrix here, F11, F12, F21, F22, acting on, and now I've added little subscripts to chi, and there's a reason for that, right? You could have, the way we probably, well, we could have done it this way. We could have put this down as C1, C2, right? However, I want to get used to the idea of seeing chi sub A, because eventually in quantum field theory, you use these chi sub A's, and you use things like chi adjoint A dot in something called the van der Waerden notation. So I'm going to go ahead and just label the matrix elements of the spinor chi with a subscript on chi. So now we understand that we're now considering our operators to literally be matrices. This works really well when you're dealing with finite dimensional vector spaces in quantum mechanics. It works a little more abstractly for countably infinite dimensional vector spaces in quantum mechanics, but it's really tight for finite dimensional ones. So this operator now becomes, I guess I could even identify it as an operator with a little hat or something, but it's pretty clear what's going on. So this operator is now a matrix. So we need to have these four numbers specified. But we definitely know that we know how to operate. We know the arithmetic of matrices. That's what we're exploiting here. And we end up with, this is the column vector that represents chi prime, right? So chi prime is equal to this thing. If all I know is the matrix, I can develop this. And literally, just so to be clear, chi as a spinor is chi sub 1 acting on the basis spinor, chi sub 2 acting on the down basis spinor. And another way of writing this would be chi 1 alpha plus chi 2 beta, where I replace these spinors with these letters. Like this letter alpha represents the basis spinor. This letter beta represents the basis spinor. The problem with that is that now I've kind of, by doing that, and you see this done a lot, you see these basis spinors represented by letters. And of course it's true, but you're kind of back to where you started here in the Dirac formalism, right? Where you've got kets going on, right? But there is, from time to time, it is useful to break out these basis spinors as alpha and beta, especially when you want to focus on just these numbers. So keep in mind that they do that. These aren't bras and kets. These are just names of the basis spinors. But once you convert the basis spinors to names, you lose the ability to execute the addition arithmetic. But that is something you see a lot. But the point here is that the components are going to be given by chi with these subscripts for now. So it is true that this is useful when I want to talk about operations on just the basis spinors, and I want to keep from having to write down column vectors for some reason. So I do know that the operation of F on a basis spinor alpha, which is the up basis spinor, will give me some alpha prime, and based on this arithmetic up here, using the 0, I realize that f on alpha prime is f11, f21. And there I have to now write out the whole spinner, right? And likewise for beta, it's f21, f22, right? So I can show how the point of this being that if you understand how these operators act on the basis spinners, then you understand how the operator is going to act on every spinner. And this is just a statement of the operators acting on the basis spinners. To be true and pure to the notation, it would have been fine to just literally write out 0, 1 here for alpha. But the book I use for this didn't. They felt the need to enter the Pauli formalism and then just give names to these two component vectors, right? So it's kind of weird how you do what's typographically convenient, right? And on this whiteboard, it really doesn't matter much. But it is true that these guys still have adjoints. So A adjoint is 1, 0, B adjoint is 0, 1. You don't see complex conjugation because the components, the complex components are just 1, right? So there is no need for complex conjugation. This is a real number inside. And but we can look at the complex conjugation of, or the adjoint of A prime, right, which is the adjoint of F acting on A, which is you flip the order and you adjoint both of them, so it's A adjoint, F adjoint, and so now you know that the adjoint of F operating on one of these basis vectors is given by these complex components of the matrix we use to define F, right? F doesn't mean anything until we know what these matrix elements are, right? That's the whole thing. And that's true in any formalism, right? Because you need to know what these numbers are. If you know the state, you're going to know this number. But if you don't know how the operator works, knowing how the operator works is literally knowing what these numbers are. That's what knowing how the operator works means. And in the two-component formalism, it means knowing the literal matrix elements. And as a reminder, we call these guys here matrix elements also, despite the fact that this formalism is not a matrix formalism. Although it's very close, as I pointed out here, right? This is very close to being a matrix formalism. So now we talk about, what about the expectation values of an operator? Well, those expectation values in the Dirac formalism are given very simply by these matrix elements multiplied by these complex numbers, right? And these complex numbers are not conjugate of each other because you're summing over m and m and the letter m and the letter n. And so this and this, they'll be conjugates of each other when m equals n, but not always. So the diagonal elements of this matrix will end up having, end up coming out to be real. But for the off-diagonal elements, it will not. So we're expecting, so the point is, but our expectation value for an observable should be real, right? And that's going to put a constraint on F, as we'll see in a moment. Okay, in other words, right, the diagonal elements, when m equals n, this is real, right? So, but this we have no constraint on. So it's never necessarily the case that this sum is going to be a bunch of real numbers, or that, for example, the complex parts will disappear. Ergo, this might be complex. However, the expectation value presumes, just by looking for something called the expectation value, means you're looking for something that you can measure, right? If you're expecting a measurement, you've got to be able to measure it. And that means F must be an observable. Therefore, this must be real. So there's got to be a constraint over here that forces this to be real, right? If we just have arbitrary numbers here, clearly this has no guarantee of being real. So in the Pauli two-component formalism, the way we write down our expectation value is like this, right? This is the matrix mathematics that mimics this Dirac formalism process, right? We have the operator acting on the state, and then we take that resulting state and we take its inner product with the adjoint of the state, right? And that's how we end up with these. That's how we end up with the the real number, right? This will end up being a real number through this process. I'm sorry, this will end up being a number, right? And we're going to have to find a way to force that number to be real. And the way we do that is we say, well, we're expecting if this number in here, if this thing inside turns out to be real, then this adjoint's not going to have any effect on the result, right? So let's just take the adjoint of our answer, which is not difficult to do, and the adjoint of this is simply this guy, right? It's the adjoint of f, and it turns out when you swap these two and take the adjoints, you get the adjoint of the adjoint, which is the normal thing, and then the normal thing's adjoint is the adjoint. So the only thing that really happens is you end up with the adjoint of the matrix inside, and the adjoint of the matrix inside is the transpose conjugate. So this number here must equal that number there, and the only way that can happen is if the diagonal elements are real numbers, and if f21 equals f12, which is all just another way of saying we've rediscovered the fact that this must be Hermitian. And it's based on the fact that our expectation value is supposed to be real. And okay, so that's the two biggest, the biggest points of the Pauli two-component formalism. We've discovered the basis vectors of the two-component formalism, and we've discovered, well, these basis vectors here, and we've discovered how operators have to work. They have to be 2x2 Hermitian matrices, and we're using regular matrix mathematics here. In general relativity, people constantly try to find a way to make sort of matrix mathematics really work, and I've never seen it work very well. You're always left with, you really are stuck with the Einstein formalism. You end up with linear algebra objects that just don't fit the normal prescription for matrices. But in quantum mechanics, it works great. But the idea here, the point of this lesson is to slip between these two seamlessly, right? You have to understand, I mean, this is sort of a matrix formalism as it is even in the Dirac system. These guys are still called matrix elements despite the fact that we don't literally operate with them as matrix elements. And so that language sometimes trips people up. It tripped me up for a little while. And we still have the notion of operators exactly the same way as the postulates demand. Observable operators have to be Hermitian, and we kind of demonstrated that a little bit through this matrix formalism analysis. All right, so that's it for this stuff. I think I'm going to leave it there for today. We covered some important topics. We sort of made this one-to-one correspondence between these things. I think that's good. The next step is to start getting into the Pauli spin matrices, which have to do with rotations of these spinor objects. And that's a kind of a complicated idea. The idea is that once we have established our spin, I guess that would be back here. Once we've established that our spin operators are going to operate on these things, we have to sort of understand how do we write down these spin operators as matrices. And this is all derived from the notion of rotations. So we're dealing with rotations in three-dimensional space of these spinors, which are these complex two-dimensional row vectors. So we have to get a handle on what that means and how that works. And this is a little bit of a story because it's derived from the notion of magnetic moment and some experimental results on magnetic moment and attributing magnetic moment to the intrinsic spin angular momentum of an electron. And magnetic moment is a vector in three-dimensional space. And as a vector in three-dimensional space, it rotates using a very simple process of matrix multiplication. But we have to sort of bootstrap that into figuring out a way to rotate these two-dimensional spinors in three-dimensional space. and the technical way of saying it, we need to represent these rotation operators in our spinor space, and we need to represent the rotations. We need to find operators that execute rotations of these spinors, and that process is actually pretty complicated. But we're going to hack through it because we really want to understand the origin of the Pauli spin matrices. We don't want to just throw them down and say, oh, there's 3 matrices, they're the Pauli spin matrices, and they represent S. It is easy to do. We can say, oh, look, I can show you a matrix that when operating on 0, 1 gives me 1/2 H bar and 0, 1 back, right? Trial and error, you can find matrices that do this. But we want to sort of go to the core and derive it from first principles. And we're going to do that in the next lecture. So I'll see you then.